Oh, perfect.
That's good.
All right.
So next speaker is Brad Cavallo, Cramer Fish Sciences.
Is that working? You know, before I got up here to the front of the room, I was imagining this was like a modern little push button thing where a light would come on or something, and it's more like kind of a Star Trek control console kind of button where it's click, but it's working. So here we are. So this idea that thank you. This idea that net flow has an effect on juvenile salmonids has actually been around for a while. If you look back at some of the earliest survival studies in the Delta, they talk about it. I think where it really came to a head is with the 2009 biological opinion, which implemented some new standards for net flow, or the ratio of inflows and exports, to protect juvenile salmonids. So that kind of brought a new level of attention to it. And at that time, DWR asked me basically, okay, here's this problem, here's this idea, this hypothesis that net flows in the form of OMR are an important driver of juvenile salmonid behavior and survival in the Delta. Go throw the data at that. Let's test this hypothesis. And so in the last 4 years, I'm really lucky to have been able to put a lot of effort into doing just that. That is, approaching that hypothesis with the data that was available. That said, DWR supported this work, but DWR, and I've interacted with DWR staff a lot kind of through this process, but this is me talking here. This isn't DWR talking. And I also want to add, for folks that have participated in this in one way or another, I am a member of the South Delta Research Collaborative, which I think Lee mentioned earlier. So this work has benefited from that discussion, lots of other collaborative discussions. And the folks that work in my Auburn office with me, Jenny Melgo, Steve Zoig, Travis Hinkleman, Paul Bergman, David Delaney, they've done a lot of the work behind the scenes to make this stuff come together. So I wanted to acknowledge those folks. So the emphasis on this work, for me, my approach to it is to really look at sort of the mechanistic, there's a mechanistic underpinning that should be behind this hypothesized relationship between OMR and juvenile salmonids. So trying to get at that. That's what I've been trying to do. So this work has culminated, or is in the process of culminating, in 6 different publications. 2 of these have been published, one's been accepted, a couple are in review, and one's still in preparation. So the stuff I'm talking about today touches on this stuff variously, but there's a lot of kind of new emerging work here, and I'd be happy to share all of these with you guys with the understanding that I think there's some public disclosure thing which might be problematic for the documents that are in review, but we'll figure that out later, I guess. Okay, so the first thing I think we need to discuss is juvenile salmon versus Delta smelt. I think there's been some confusion, sort of an assumption that they respond equivalently to flow conditions. I added this conceptual model. This is my conceptual model for the Delta. I threw this in after everybody else was talking about it. I didn't want to be left out. The key thing to take away here, and I'm going to provide some more explanation of this, I think for juvenile salmonids, the key thing to recognize is that they behave in the Delta in 2 very different capacities. They're either migrating, where they're swimming to get somewhere, or they're holding and rearing. And the things that they're vulnerable to in terms of growth and predation and mortality are really different depending on which of these they're doing. So I'm going to explain a little bit more about what I mean there. So here's your Delta, your picture of the Delta. This is from some BDCP document that I swiped off the internet. And here's my gross simplification of what happens to smelt in the Delta. So they smelt reside, they're a pelagic organism, right? So they reside in this body of water that is out there in the Delta. They're feeding and doing their thing. Tides, as they come in and out, will tend to push the smelt in their sphere of water around. And if there's a net flow, they could get pushed somewhere maybe where we don't want them to be. So that's sort of the conceptual model for Delta smelt, and recognizing that there's a lot of subtleties for them, but that's the idea. Maybe particularly true for an early life stage of Delta smelt. So salmonids, okay, totally different. Here's the rearing phase of things, as best we understand it. They're not going to be holding out in the main river channel. They are going to sit up on some structure, probably a shoal, someplace where they can feed and rest. And they're going to hang out there. They're going to be oriented to something. They're not going to be out in the open water sloshing back and forth, except when they're migrating. So the tides, that's what these black arrows here are intended to represent. The tides might shift. The fish, will move around a little bit in there, but they can stay right where they are with tides going in and out if that's what they want to be doing. So what about when they go to migrate? Well, the idea is that they can take advantage of an outgoing tide and move along with it, go somewhere else, assume another rearing position, and hang out. The tides switch. They can hang out a little more, wait for the tide to go back to an ebb, and then they move on their way. So this difference here, I think, really changes our expectations about how vulnerable juvenile salmonids are to net flows in a tidal environment. And that's really the key here, tidal environment. In a river, we all understand what the effects of flow are. It's mechanistically, it's very easy to understand. In a tidal environment, net flow means something entirely different. Okay, so just to recap there, juvenile salmonid behavior in the delta, when they're rearing, and this is something, we call this non-natal rearing. I started my work upstream. That's what we call basically when the fish are rearing anywhere other than where they spawned. So, and we know that they do this, right? They come out of the gravel, they rear for a while, they head downstream, and then they do all kinds of crazy stuff. They swim up into other tributaries, they go into backwater ponds. They're looking for places to rear. So fish aren't robots. They don't just go downstream in one direction and go to the bay. They do other kind of weird things. And in that process, they end up in a lot of strange places. When they're doing that, when they're looking for rearing habitat, they're going to be oriented to shallow edge habitats, and they're, in the delta at least, they're going to be feeding on benthic invertebrates. I'm sure back when there was neomysis, they probably ate a lot of those, but those are gone. There's really no sizable zooplankton available for juvenile salmonids to eat in the delta. So if they're feeding on benthic invertebrates. Then when they're migrating, they're moving quickly in a directed fashion, it would seem. And for the acoustic telemetry studies, we're seeing that most of the fish can get through the delta in a week. Sometimes more, sometimes less. That's directional swimming, fast directional swimming in a tidal environment. And then lastly, this point about these fish have an ability to navigate. And this is often overlooked, and I hear it repeatedly, this idea that net flow is the key, in a tidal environment, is the key to these fish being able to find their way through. That's a hypothesis. It's worth considering. But if you look at the literature on this, what you find is that these salmonids, and probably a lot of fish, have an ability to find their way through environments where there isn't a strong flow cue. And the idea, we don't know exactly how they do it, but it's some combination of orientation to the sun position, to geomagnetic field, and probably chemical cues in some cases as well. Salinity might be an important one. So this idea that they need a net flow to get out is a little bit odd. And to make the point, in case you're still doubting me here, this is the historic delta, which was riddled with these tidal channels, right? And the fish love these tidal channels. If you go to other estuaries, the salmon are in these heavily. Well, these tidal channels don't have a net flow. They're tidal, right? There's no net flow coming down. But, evolutionarily, obviously, juvenile salmonids were able to find their way into these and then find their way out again in the absence of net flow. So obviously there's something going on here for these fish finding their way around that doesn't include net flow in a tidal environment. Okay, so let's talk a little bit more about net flow or the alternative, which is instantaneous velocities. What do those things look like in the delta, and what do they mean to fish? So we've done a bunch of analysis on this using DSM-2 hydro simulations that were provided by DWR, and we've actually put all that data into a web app. The address for it is right here, and actually this address is on all the subsequent slides as well. So with this web app, you can go in and select whatever channel you're interested in, whatever route you're interested in the delta, and the map will help you to kind of figure out what those are. And at this point, we've represented all the major migratory routes that we've observed fish using from the acoustic telemetry studies. We haven't included a lot of the really small routes. And this does include the South Delta, too. It just got cut off in this picture. So when you go into that software and you pick out a channel, you can get data that will look a lot like this. So what I'm going to do here, we're going to take a little walk through the delta looking at the velocity profiles. So you're going to see a series of figures that all are laid out similarly. So there's a stacked graph with different Vinalis flows on this side, and then there's a frequency of observations of velocity categories, and that's what's on the x-axis here, and then this map on the top kind of tells you where you are in the delta. And so what you see here, and this isn't terribly shocking, upstream, as inflows go up, in the San Joaquin River, the velocity profile changes pretty dramatically at this location. And just to help you interpret a figure I'm going to show a little later, we've calculated something called the density dissimilarity index on these profiles, and I'm going to try and show you some numbers just so you have a feel for how to interpret this. And the density dissimilarity between 3,000 and 6,000 CFS is 0.75. So let's move downstream a little bit. Now we're below the head of Old River. We're kind of, I think, just upstream of Stockton. And here's the velocity profile. And you can see that, at these lower flows, we're starting to see less differentiation here, and we're seeing a very strong tidal signal. Higher flows, we are seeing an effect of the river inflow and pushing those velocities to be more positive. Let's go downstream a little further. This is just upstream from Turner Cut. And again, we're seeing this continuation of the same pattern where the velocity profiles are starting to become more and more similar among the four different levels of inflows. Just for comparison, the density dissimilarity between 3,000 and 6,000 CFS, in this case, is less than 0.25. So at this point, they're really not very different by that metric. Okay, moving downstream further yet. Here, we are basically seeing that there is very little flow signal in terms of the velocities that are present out there. You don't see much difference between these profiles with different inflow levels. And I was struck when Pat was talking about her work earlier that this really does seem to line up in a lot of ways with what we're seeing out there in the field, where we have a flow signal that changes the velocities. We see a response in the fish. But when the fish get to these areas where it's tidal, the flow just doesn't seem to matter anymore, and it's all just about velocities sloshing back and forth. So there really isn't there isn't a mechanism to expect that inflow would alter the survival of fish in this area, within this range of flows at least. So let's go down a little bit further yet, and same relationship. We're not seeing much differentiation in the velocity profile with different flows. Okay, so now I got to tell you, I've been going through these, and you maybe have noticed some little things peeking out on the edges here. The other part of the data here that hasn't really even shown up is different export levels. So the export that is equivalent to 3 different OMR levels is plotted in each of these velocity plots. And so where it starts to come out is when they start to spread. And you'll see what I mean here as we move. I'm going to march us down Old River. And you'll start to see what I mean, where the export effect really becomes visible. But before I leave this one, I want to point out here that our density dissimilarity is quite low here, and that this is a place where when you're pumping a lot, you get a very negative net flow, okay? But you look at this velocity profile, and it's very hard to see a difference. So you have to ask, there may be a strong negative net flow, but what is the fish actually experiencing out there? The fish is experiencing these velocities, to the extent that a one-dimensional model can provide a realistic representation of velocities, but it's an approximation. Okay, so now we're going down Old River. You can see where we are on the map up here. And, we're starting to get a little bit of color peeking out here. So what this is saying is that as you get a higher export level, there's starting to be some differentiation in the velocity profile, and our density dissimilarity is going to start creeping up, you'll see. Okay, we're getting further downstream. Now you can really see what I'm talking about. Different export rates. Higher exports are shifting the velocity profile slightly to the left. And we're up to a density dissimilarity of 0.3. Further yet, we're getting more differentiation. And also to note here that there really isn't much effect of inflow. And maybe this goes without saying, but OMR is a function of San Joaquin River inflow and export. So really what we're looking at here are the two components of OMR and how they vary and how they affect velocity profiles in the delta. So we're up to a density dissimilarity of 0.4 here. Jumping much further down, you can see we're getting some really big differences here in the velocity profiles, and this is a big density dissimilarity, relatively speaking, up to 0.75. So this data that I'm plotting here is all available in that web app for all the channels that you can see in these maps that are available in DSM-2 Hydro. So, I'd encourage folks to poke around with that if they're interested. Okay, now, so I've been showing you the density dissimilarity indices, and this is a plot looking at basically plotting those in the delta. So for each of these, what we have to do is compare 2 different conditions. So this first one is a comparison of the velocity profiles at 3,000 CFS and at 6,000 CFS without any change in OMR. And what you can see here is that there's parts of the San Joaquin River main stem where an increase in flow from 3,000 to 6,000 really makes a big difference in changing the velocity profile. But then it kind of gradually attenuates, and you're pretty much back to where it doesn't make a whole lot of difference. And we also see some effect of that even in the old river corridor as you approach the facilities. And again, I was struck by Pat's data. I hadn't seen some of that stuff before, where she's seeing some evidence of this is where you're seeing the flow effect on survival. And I think that mechanistically it makes a lot of sense, right? Because that's where the flow, the inflow, is changing the velocity profile. So what's the effect of exports on the velocity profile? Well, it looks like this. You can see that we get a very strong effect very close to the facilities, but then it attenuates as you get further out. So this probably means something to fish too, and we're still working on trying to understand that. But I think this perspective on the velocity profile provides a more salmon-centric understanding or mechanistic interpretation of how exports could be affecting these fish as they migrate along than does net flow. Net flow gives you a very different picture. Okay, let's talk a little bit about fish routing at junctions. This is in a paper that's in review currently. I think I asked you guys to review it actually, so you might see it at some point. Took a little different approach, and I've got to credit John and Russ that this analysis that I did was entirely inspired and made possible by your guys' work. I took a little different angle on it, but you guys laid the foundation here. So there's 11 different junctions in the delta. This gray area here is what I would call the interior delta, and we've really been focused on looking at these junctions and the predicting the rate at which fish, migrating juvenile salmonids, enter these and how that is affected by operations. But there's a lot of data from other junctions that help us to develop this predictive relationship. I can't go into a whole bunch of details in this presentation. It's in the manuscript, but I'm just going to tell you that we developed a proportional flow metric by analyzing DSM-2 hydro hindcasted data for each of these junctions. So there's six junctions that we had routing data available for from various acoustic telemetry studies, including Russ's stuff. And so then we were able to go back and use DSM-2 hydro to calculate the flow proportion. And we got this relationship which explains about 70% of the variability in where fish go. So we feel like we have a flow routing metric that I'm sure it doesn't meet John's high standards, but for a field ecologist like me, this is like, wow, this is amazing. I've never had such a good relationship. So it's a good start. I suspect we could get it up a lot higher. There's a lot of detailed site-specific things that affect what you're seeing here, but this is a good kind of a gross pattern, I think, for us to begin with in the delta. What else to say about that? So what we did then with this relationship, somewhat validated with these studies, these 41 releases at 6 different junctions, is we then took this relationship. Oh, I know what I wanted to say. It isn't one-to-one. The fish are not going in one-to-one. It's something less than one-to-one. So there's other factors at play here that are causing the fish to not go into the junction at quite the rate we would expect if it was strictly just based on flow. By the way, this is not net flow. This is a daily flow proportion, kind of a roll-up of 15-minute time interval steps. And so this is all described in the manuscript, how we did that. Seems like it might be useful. So you take that data, and then or take that predictive relationship, and then you can make some predictions about entrainment at different junctions in the delta. And I'll try to summarize this as quickly as I can. So these are at 3 different export levels. And so these ones that are in the middle here, Turner, Columbia, Middle River, Old River, Fisherman's Cod, Jersey Point, these are all tidal junctions, okay? They really are not affected by exports, and they're also not affected by inflows. Right now I'm only showing the effect of exports, but we had this relationship with inflows as well. These are just not sensitive to exports or inflows. Georgiana Slough, very much consistent with what we just heard from Russ, actually, Georgiana Slough is not affected by exports at all. And that's kind of what I was getting at earlier. We're talking about net flow may have some importance on the Sacramento River, but it's net flow driven by river inflow. There's no effect, and correct me if I'm wrong, but exports does not change net flow on the Sacramento River or in Georgiana Slough. Doesn't. Head of Old River, it does make a difference at low inflows. which is kind of interesting. But here's where head of Old River is different. When flows in the San Joaquin River go up, the proportion of flow that goes into head of Old River increases. So it's the opposite pattern of Georgiana Slough. So in any case, this is a sort of a management interpretation of the data that we've seen from the field. Okay, let's talk a bit about entrainment losses, because this is another kind of piece of evidence we have about what's going on out there. And again, this is a paper that's been accepted. So Lee talked about this stuff earlier, but he used a different data set, and he was speaking about winter Chinook and spring Chinook and steelhead, and basically that was all raw salvage for the most part. So the difficulty with raw salvage is that we can't actually identify where the fish came from or even what race they are. So it's all based on length criteria, which we know is not terribly reliable. For winter Chinook, I think we get about 50% of the fish we call winter Chinook are actually winter Chinook, so it's not terribly reliable. For spring Chinook, actually, there isn't really even a spring Chinook category. It's sort of a size category of larger juveniles, but it undoubtedly includes lots of fall run Chinook and other races of fish that just happen to fall into the size slot that could be called spring Chinook. The other big problem with it isn't just identifying the stock, it's knowing how many fish you started with, right? And somebody asked the question about, well, what was the spawning like? How many, what was the escapement, or what's the juvenile production? And that's actually a lot harder to get at for some of these stocks. So the solution to all that is to use codewire tag releases, which we have lots of, and analyze those to look at what is the loss rate of codewire tag releases in relation to exports. So I'm going to march through a few different examples here. So these are all fall run Chinook. We've grouped these by race. Fall run that are released from Coleman. So these are released way upstream in the Sacramento River. And then fall run that are released somewhere not in the Delta, but just upstream of the Delta on the Sacramento River. And this is the proportion of loss. This is expanded for pre-screen mortality, including at Clifton Court Forebay. And what we see is that the proportional loss for fall Chinook is relatively low. We get some fish loss even when we're pumping a little, and when we pump a lot, we might get a little bit more. But in general, for fall Chinook, the loss rate is quite low. For winter Chinook, it's different, and this is really interesting. So we have the average loss rate is 0.05%, and we see, at low exports we get some loss, at high exports we get some loss. You can fit a line through here, and it is a positive relationship. So it's saying when you pump more, you're going to get more fish. Makes sense, right? In a lot of ways, the export facilities function very much like a big sampling device. Catch per unit effort. You sample a greater volume of water, you're going to get more fish. What we're interested in is why. Is it because we're pulling fish in, or is it just a matter of sampling? And that's what we're trying to get at here. So for spring Chinook, we don't have as good a data set that would allow us to make these comparisons of the response of loss relative to exports. But just kind of grouping them together, the loss rates for spring Chinook, both hatchery and wild fish, are really, really low, lower than for anything else. And this is a large sample of fish, 6.8 million for hatchery and 2.8 million for wild fish. San Joaquin, okay, well, San Joaquin fish, if there's no barrier, they're heading down the San Joaquin River. If they turn down the Old River corridor, they're right there where they're going to get directly exposed. So the exposure is high, and the loss for San Joaquin codewire tagged fall Chinook can be quite high. Interestingly, we don't have a lot of treatments with high exports, and I think that's just a function of what Pat was talking about earlier with the VAMP study design, because a lot of these releases are from VAMP. Okay, so this is the part that's really key for management. Now, folks have talked about OMR, often presenting an analysis that looks at OMR, and that's good, but what you really need to do is compare OMR relative to other explanations, right? I mean, we're trying to test a hypothesis here. Is OMR a better predictor of loss than the alternatives? So we did that for this analysis, and what we found was that, in fact, exports is the best, far and away, is the best predictor of how many fish you're going to get among these different codewire tag groups. OMR, you don't need OMR. You can do it with exports alone. So what this suggests to me is that the OMR net flow effect mechanistically isn't supported by this. There may be other things that are going on, but for whatever reason, OMR isn't a key driver here. You can explain salvage mostly by just how much you're pumping, and irregardless of how much water is coming down the San Joaquin River. Let's talk a little bit about OMR survival, and I'm almost done, I think. help me out here. There's a bunch of stuff on survival. Pat touched on it earlier. I'm going to touch on it a couple of things. David Delaney from my office is going to give a presentation tomorrow on the results of the 2012 stipulation study, which specifically looked at steelhead smolt behavior in the Central Delta in response to different OMR levels. I want to touch on a couple of the VAMP acoustic telemetry studies, expanding on what Pat talked about earlier. One other thing to note, the Newman 2008 is the definitive analysis of all the Codewire tag experiments from the San Joaquin River. And Pat had the figure up there earlier, and you may have missed it, but there was a positive relationship with flow. Again, I think that's because of the change in the velocity profile in the main stem San Joaquin River. That study also showed a positive effect of exports on survival. And we've been kind of dismissive of that. Well, that can't be. That doesn't make any sense. So keep that in mind. Okay, so VAMP acoustic survival studies from 2010. Of all the fish that survived to Chips Island, 39% came through the various routes that Pat talked about earlier. 61% came through CVP. They were salvaged fish. So the survival is horrible. I'm not even giving the total survival estimates here, but salvage through CVP, this is how bad things are in the South Delta. CVP salvage is the major driver of fish, or the major cause of fish surviving to Chips Island. Here's another little nugget here, and this is really interesting. So we do have some estimate of the fish that came by CVP and headed north. So they were at this junction, at this receiver network here. The probability of those fish that made it to here surviving to Chips was 0.01. So hardly any fish that were heading north made it. The ones that made it, who went into the Old River Corridor, were ones that got salvaged. Okay, so 1 year, 2010, big deal. We see almost the exact same pattern in 2011. I haven't seen the 2012 data, so I don't know what it says, but this seems like a fairly consistent pattern. So here's the really interesting thing about this, okay? So you would look at this and say, okay, that's OMR, like there's a net negative flow, and the fish are trying to get past, and they're getting stuck, and they can't make it, and they die. The thing is that both of these years we had low exports and positive OMRs. We had good flows this year, and the fish were still not surviving heading northward from the facilities. So this suggests to me that things are bad in the South Delta for juvenile salmonids, but they're bad seemingly regardless of what the OMR is. So the question is, can we make this better by tweaking OMR? I don't know, but this was a positive OMR condition, and things were terrible. So it's something to think about. So let me recap. Juvenile salmonids, I think, are less vulnerable to net flow in this tidal environment than our smelt, just because of their behavior. I don't think net flow is a good index for changes in velocity, and the data I showed in the velocity profiles, I think, highlights that. And this is a key one here, this next one. Exports have a different effect on velocities than San Joaquin River inflow. And this is actually my biggest gripe about these indices of net flow, like OMR and IDE or E to I, is that they create this impression among managers and biologists that these things are substitutable. Like, well, if you can't get more inflow, well, then just turn exports down. It doesn't work like that. You can see from the velocity profiles that when you change one thing in one place, it has an effect, and when you change it somewhere else, it has a different effect. So if you want to increase survival on the main stem San Joaquin River, doing increased inflows is a great way to do it. Changing exports, not so much. And lastly, the interior delta survival is poor, but it doesn't appear to be related to OMR. OMR may be important in a different kind of delta where the habitat was good and we didn't have an impaired food web. You might see a lot of sensitivity to OMR, but the way things are right now, the habitat is such that whatever OMR effect there is just being masked by the very high mortality rate. I think that's all I got. Yeah, I'm done. Thanks.
Time for a question or two?
Stumped me.
Yeah, thanks, Brad. I enjoyed your presentation. This question it's for really everybody, not just specifically for you, so don't feel like I'm beating up on you.
Okay.
If I think about fish sensory systems, and I ask, well, what kind of hydrodynamic variables can they actually detect? There are things like small-scale velocity pattern and accelerations, both spatial and time-dependent. But they don't have any mechanism for computing total flow, so they don't know what it is. So when you use total flow, is a variable, that's primarily because of human interest, not because of its direct connection to fish in any kind of first principles way. And that's really great that you're worried about the decisions that humans make. But on the other hand, you have to acknowledge what fish are doing too, because the solutions to all the problems involve interfacing with the fish, which neither the work I saw you present or most of the other work, in fact all of it, didn't really do. So I'm concerned that there's whole categories of solutions that might be out there, but the way the problem is being formalized prevents you from finding that solution. What's your pushback?
I couldn't agree more. We're not addressing. I didn't address the OMR hypothesis because I thought it was the right way to, or the best way to use our resources. I am investigating it because it was a regulatory requirement. I think we're asking the wrong question. I really do, and I think a lot of other salmon biologists in the Delta would tell you the same thing. But this is where the resources have been put because that's where the management nexus is right now. It's a problem.
Okay, if you guys are satisfied, we'll take a break now. Oh, wait.
I am. What are the right questions?
Well, I think we have lots of opinions about that, but I have to think that I think Matt did a nice job earlier, and it's about habitat. The habitat is altered. It's nothing like what it used to be. We have non-invasive fish everywhere. There's not a lot for the fish to eat. So, saying that is easy. It's probably true, but it leaves us kind of in a pickle about what to do about it. BDCP is supposed to be about that, but that's a long-term plan. In the near term, I think there's some things we could be doing. I think we could be doing a lot more, doing some experiments with habitat enhancements or habitat actions, and I think that's where a lot of us would like to see the research and management effort going into those kind of things.
So let me follow-up question, Brad.
Yep.
So if it's habitat, one thing that's always puzzled me about all of the habitat discussion is the fact that the habitat in the San Joaquin side is just as crappy now as it was in, say, 1960. Salmon didn't seem to be doing so badly in 1960. Is it just a long, slow decline, or is...
I think the food web has changed. It really has. And actually, I think our project operations have contributed to that in some way. I mean, we're conveying more water. It's odd. We convey less water in the spring now than we used to, but we convey a lot more in the summer. We have invasive species. I think the pod decline, I don't think is independent. We haven't really tried to study it, but when you have a big change like that in the food web, it's affecting juvenile salmonids. So I think it's a lot of things. Did I answer your question?
Yeah.
Okay.
Brad, you'll be around later too?
Yes, I'll be here tomorrow too.
Okay. Well, it's time for a break. We're going to take 15 minutes and be back at 2:45, and a couple more talks, and then some time for general discussion.